Okay, in this video, I'm going to talk about one of the more amazing ideas in mathematics, the idea that of the golden ratio. So first, let's start by kind of defining what the golden ratio is. So suppose I have a line segment. What I want to do is I want to divide this segment in such a way where if I have two sections, the large section A and the small section B, I want the ratio of the large section A to the small section B to be the same as the ratio of the whole line segment, so that's A plus B, that's the whole line segment, to the larger piece, A. And if this property holds true, this is once I find this ratio, I'm going to call this phi, and this is the Greek letter phi. And some really interesting things come about when we look at this. So let's go ahead and let's actually take a look at this equation here and see if we can't kind of figure out what phi really is. So I have A over B is the same as A plus B over A. And if I take this fraction right here and I break it apart, I have A over B equals A over A plus B over A. Well, I know A over A is 1, so I have A over B is the same as 1 plus B over A. So now we defined A over B as phi, is this Greek letter phi, and that means that if I take this expression right here, what I'm really saying is that phi equals 1 plus 1 over phi, because B over A is the inverse of A over B. So to take the inverse of that expression, I just put it over or put it under 1. So now I have this really interesting kind of mathematical equation where phi equals 1 plus 1 over phi, and that's kind of cool because if you take the inverse and add 1, you get the same number. That's a really interesting mathematical property. So let's take a look at this further, and if this is a little bit more advanced than you're intending to go with it, you can use this for your own knowledge. But we have this equation, phi equals 1 plus 1 over phi. And if I want to really kind of get all my phi's together and create an equation where I don't have 1 in the denominator, I can multiply both sides of my equation by phi. So I can distribute that in, and what I end up getting is I get phi squared equals phi plus 1. So again, this is really an interesting concept where you take the square of a number and it's the same thing as 1 more than the number. So this equation ends up becoming a quadratic equation, which if you want you can solve. Phi squared minus phi minus 1 equals 0. And I'm not going to go through the quadratic formula in solving this, but what you end up getting is you get that phi is the same as 1 plus or minus the square root of 5 all over 2. So these are the values for phi, and because originally we started looking at a line segment, we're really interested in the positive value. So this gives us this golden ratio, this number phi, this special number. Phi is 1 plus the square root of 5 all over 2. So now, examining and evaluating this number, we can see because there's this square root of 5 embedded in here, which is an irrational number. Phi is an irrational number, and that means that it cannot be expressed as a quantity of two integers. And if we evaluate the decimal expansion of this number phi, we end up getting that phi is equal to 1.618033 988, and infinitely more numbers that don't repeat in any kind of sequence. Really, what we do is, if we're looking to kind of abbreviate this numerically, we say that phi is really approximately equal to 1.618. This is kind of like saying that pi is equal to 3.14. It's not really equal to 3.14, but for our purposes, it serves a purpose. It helps us in the computation. So other than solving a quadratic equation, there are other ways that we can get this number phi to really emerge. So let's take a look at one of those now. This is, I think, a little bit more accessible for students. So what we're going to do is we're going to look at the Fibonacci sequence. And the Fibonacci sequence is when you start with the number 1 and then another 1. And this sequence goes by adding the two previous terms together, two previous consecutive terms, to generate the next term. So I have 1 and I have 1. 1 plus 1 is 2. So now I have 2 plus the previous term 1 is 3. 3 plus the previous term of 2 is 5. 5 and 3 is 8, and so on and so forth. So we have this really interesting sequence of numbers that is really kind of special when you take a look at it. So I know the question is, where is this number phi in the Fibonacci sequence? Well, if you take any two consecutive Fibonacci terms and find the quotient or the ratio of those terms, the larger the numbers get, the closer the ratio gets to 5. So if I look, for example, say at, well, the next number here is 13. Let's look at 13 over 8. 13 over 8 is about 1.625, and remember, so recall phi is 1.618, roughly. And 1.625 is pretty close to 1.618. So if we look at bigger Fibonacci numbers, so another larger Fibonacci number is the number 987. And if I look at 987 over its previous Fibonacci number of 610, when I divide those two and get that quotient, I get 1.618. Which is our approximation of phi. And the larger the Fibonacci numbers, the closer that my decimals beyond the thousandth place will start to match those of phi. So Fibonacci is a really interesting way to examine this, this special property. Interestingly, this pattern, this number phi, this Fibonacci sequence, even appears in other places. For example, if we have Pascal's triangle, which is created by summing the two terms above it to get the next term in the row. So 1 is on each side, 2 and 1 is 3, 2 and 1 is 3, and 1 on the end, 1, 4, 6, 4, 1. And what I'm going to do here to find the Fibonacci sequence in this, just another interesting mathematical property of phi, is if I look on the diagonals of Pascal's triangle. So if I look here, this diagonal only has the number 1. If I come between these two through this, again, I hit 1. Here are 2 1s here, which is 2, that Fibonacci sequence. The next diagonal, 2 and 1, gives me my 3. 1, 3, and 1 gives me 5, and so on and so forth. I can keep going down the triangle infinitely, and it'll generate the Fibonacci sequence. That's just an interesting pattern. There's a lot of other patterns that you can explore in Pascal's triangle. But that's really not the focus of our discussion today. So let's go back to this whole idea of the Fibonacci sequence and the golden ratio. You can use the Fibonacci sequence to create a golden rectangle. So let me pull up some graph paper here, and I'm going to show you how we can do that. So let's start by creating a 1 by 1 square. So this is the first number in the Fibonacci sequence is 1, and what I'm going to do is I'm going to stack another 1 by 1 square on top of it. So I'm going to match the side, and I have another 1 that's completed next to it. So the first two terms in the Fibonacci sequence are 1 and 1. Now, if I continue out, now these two have created a rectangle, and this rectangle can create another square that has a side length of 2. 2 being the next number in the Fibonacci sequence. If I continue this pattern, now my side has a 1 and a 2, so I can create another square that has side length 3, which is the next term in the Fibonacci sequence. And if I continue spiraling outward, I now get a square of size 5. And I don't think I have enough space on this graph paper explicitly to go up, but 2, 3, 4, 5, and continue this up to get an 8 square, and I can create really a golden rectangle where the ratio of the large side to the small side to that of the whole kind of matches. So like we were talking about before, if I look at this rectangle right here, this rectangle is closer to a golden rectangle, and if I look at the ratio of the whole side, which is 8, so red is 8, to my larger side, I'm going to use green here, of 5, so I have the whole thing to the big side, 8 to 5, is roughly equivalent to the ratio of the 5 side, so the 5 to that of the smaller side. We'll for this one, this blue one right here, to 3. And these aren't exactly perfect. It's not a true proportion, but they're close. If I make the rectangle bigger and bigger and bigger, this golden ratio will emerge as I take the quotient of these two Fibonacci terms we saw before. Now, this rectangle has become very fascinating to people throughout history. So now I'm going to show you some examples of where this emerges. So one place that we see the golden rectangle emerge is in architecture. So here are some examples of some architectural structures that were built throughout history. We have the Parthenon up here. So we have the Parthenon. We have the Cathedral of Notre Dame here, and we have the Taj Mahal. So these three structures from different parts of the world in different periods of time, all these architects got the ideas behind these golden rectangles. And if you look in the Parthenon, you can see there are golden rectangles present in the outer area of the structure. There are golden rectangles that go along the top. So each of these guys right here is constructed in the fashion of one of these golden rectangles. The distance between the pillars is a golden rectangle. If you look at the Cathedral of Notre Dame, even the windows down here are constructed using these ideas of golden rectangles. So really, it's all over the Cathedral of Notre Dame. On the Taj Mahal, again, you can kind of see the divisions. You're really looking at where the leading lines of the structure go and the ratios between the two. So architecture is a very prominent example of where we can see the golden ratio. So now let's go back to our golden rectangle. So I'm going to really, really quickly go ahead and create this guy again, just so we can look at it. Because there's another cool thing that we can do with our golden rectangle that we've created. So that should be a 5 down here. 1, 2, 3, 4, 5 by 5. So if we start in our first square on the inside right here, and I create a circular arc that goes through the corners of each of these things, and then it kind of spirals out and around, I end up creating this, what we call a golden spiral. And this is a really, really powerful mathematical tool as well, because this spiral is seen in a lot of other places. For example, one instance that we see the golden spiral is in that of a nautilus shell. So the rate at which this spirals outward corresponds to the golden ratio in the Fibonacci sequence. Another place that we see it in nature occurring is in the patterns of a storm or a hurricane. If you look at this hurricane right here, the rate at which the wind and cloud spirals outward matches perfectly to this whole idea of a golden rectangle. Even spirals in plants contain these Fibonacci numbers in this golden ratio. So let's say I look at this flower right here, and I just want to really quickly count the number of spirals that have these light blue lines right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 is one of the Fibonacci numbers. If I counted the dark blue, which I'll leave you to do, you would also get a Fibonacci number. So these numbers appear in nature. This ratio, this golden ratio, kind of spirals out. Artists have even gone as far as using this concept in some of their works and their paintings. For example, these all are artistic illustrations that utilize the golden ratio. In the Mona Lisa, you can see lightly there have been golden rectangles that have been drawn over the portrait, and you can kind of see where it matches up with her eyes, her mouth, her nose, the rate at which the chin meets the head, meets the arms. Da Vinci was a big fan of this. You know, you see it in The Last Supper. There's some Salvador Dali paintings where it uses it. So really, this video is really designed to get you to just think about where are the different places that this occurs. Really look and analyze and find these relationships and ratios outside around you, and look for these connections that are inherently mathematical.